Hello everybody, welcome back to new lecture, and this will be the continued session for question and answer discussions for inorganic portion, where the given question is what is effective nuclear charge, that is Z effective. We should be stating the definition for Z effective, and also state Slater's rules. Here Slater's rule means it is a quantitative approach for defining how much is the net nuclear charge. So we will be proceeding here. The definition Z effective is definition here. The term effective is used because let's proceed with one example. This is one typical example for polyelectronic example, that is atomic number 12 magnesium, where the electron present in the n is equal to 3, that is outermost electron. Consider this one, where for this particular electron the attraction between nucleus and this electron is somewhat shielded or covered by these in between and innermost, that is at n is equal to 1, and in between, that is in n is equal to 2, and one another atom that is present along with this electron that we have considered at n is equal to 3. So apart from this electron, there are totally 11 electrons that are somewhat shielding this 12th electron. So here the charge exposed on this particular electron is not exactly 12, that is 12 minus something that is shielded by these electrons, that is shielded by these rest of the 11 electrons. This will be that effective is given by that effective is given by Z effective is equal to total charge minus the electrons shielding, that is sigma. We will use sigma symbol here for shielding because this term sigma refers to shielding constant. So thus, in order to prevent this attraction by the nucleus, that whatever the shielding quantitative that charge is given, that is example Q, the charge is given, that is given by sigma. So thus, moving into the Slater's rules, because here approximately there are 5 rules. That is, they are well known as Slater's rule, because this Slater's rule gives some calculative analysis for calculating Z effective. So now we'll move on for stating those Slater's rule. That is, these are very simple rules where everyone can easily remember. Before stating them, also remember one more key point, that is Z effective is always less than the actual nuclear charge. This should be the key point. Okay. Moving to the first Slater's rule, for any given atom or ion, for calculating its Z effective, first arrange its electronic configuration in the form of this given manner, where n value, that is principal quantum number, goes on increasing. Okay, initially for all n value is equal to 1, then 2, then we will separate 3 number, there 2, we will group them in S and P. For S and P separately, then D is separately kept. Here D is separately kept and F is separately kept in a single group, whereas S and P are separated as whole. This will be the rearrangement of their electronic configuration. After this, point number second, that is second point, where it says that a common sense thing. Let's take the previous example only. If you consider this particular electron, that's outermost electron, if you consider the Z effective on this electron at n is equal to 3, all the electrons before this lying between the nucleus will be contributing some kind of shielding effect. Where if you consider any one of these electron at n is equal to 2, where somewhere in the 2s orbital, in that case consider this one. if this electron is taken for the calculating shielding effect, and these outer electrons will strictly and will not be involving in the shielding effect, because they are present outside the away from the nucleus, whereas for shielding there should be presence of electrons in between the nucleus and the considered electron, where this outermost electron is not considered for shielding for these inner electrons, whereas these inner electrons are considerable factor for outermost electrons shielding effect. This should be the simple concept. Here the second statement is given as electron in a group beyond that of electron consideration contributing nothing, that is, it will be not involved in the shielding effect. This will be the second statement. And moving on to the third statement or third Slater's rule, that is, here we have segregated them into different groups that we have in the format, where the particular group is given as NS&P togetherly, and ND, NF are written separately. Here for those separated groups, for NS&P, that is NS&P, for these groups we have some kind of value analysis. Value stated that shielding constant, that is sigma shielding constant, is given as first one for this only NS and NP 0.35 for each electron in same group. If we consider 2p6 2p5, that is if we consider fifth electron of this group, and the rest of the 5 plus 2 7 will be contributing 0.35 for that shielding effect, where the another rule is 0.85 by each electron in n minus 1 shell. Here at n level 0.35 is considered, whereas just previous to that one will be given by 0.85, and the last one except n and n minus 1 shells, all the inner electrons contributes shielding effect by each electron is 1.00. That is completely they will be providing the shielding effect. So here the first condition for n 0.35, 0.85 and 1. For different kind of calculation, I also take these 0.35 and 0.85 as 7 divided by 20 and 17 divided by 20. This is just the fractional mode of this decimal form, because it will be a kind of helpful in the calculation, but it's not mandatory. You can remember like this also, but whosoever feels it's funny to remember, we can remember in this format also. Next we'll be moving with now we have completed NS and NP, so we'll be moving with ND or NF. That is rule number 4. Is for those ND groups or NF groups, because ND or NF are separately written. So here for these groups, electron shielding will be their value will be 0.35 for each electron in same group, that is at value n, and directly 1.0, that is complete shielding for each lower or inner electrons. Here ND and NF, these have two set of sub rules, and this one NS&P group has these three values. Please do remember these two rules are the very important for the calculation. And by this one more last fifth rule, that is not important, but not to neglect it, because it may not be important in all the polyelectronic, but it is very important in monoatomic or diatomic calculations, that is the hydrogen and helium like atoms, where the fifth rule says that for one of the two electrons, for one of the two electrons present in one s orbital, that is one s orbital, any atom, the contribution for another is, that is sigma is, that value is given by 0.3. Here it is not to worry that to remember all these 0.3, 0.35, 1, because you practice one or two questions, you will be making them easily identifiable, and it is a very simple concept. So moving with it for some example discussion, so the concept will be very well learned, and it may not be forgettable, because most of the chemistry concepts are volatile in nature, that they evaporate, that whatever we have learned, they will evaporate. So here for consideration, the first example will be atomic number 29, that is copper. For this particular atom, in this particular atom, calculate the Z effective for the electron present in 4s orbitals. So here first we need to write electronic configuration for copper. So this is the electronic configuration, and we will rearrange them according to Slater's rule. That is first Slater's rule, that we have to rearrange in accordance with this pattern. That is we will regroup them into 1s, 2s, 2p, and so on. So here these are the rearranged structure of this electronic configuration for atomic number 29, copper. So now we will be substituting values. For defining shielding constant sigma, where it is better that we will start from the outermost electron, because we will be talking about, or we are considering 4s electrons, where 4s electron, there is only one 4s electron. So leave that electron. So remaining electrons in the fourth shell is 0. So the fourth shell is nullified except this electron. So after this, there are totally 10 electrons in the 3d orbital. And 8 electrons in the rest of the s and that is n-1 shell. So here the values given for is 0.85 into total electrons are 2 plus 6 plus 10. 2 plus 6 plus 10, that is totally 18 electrons. And here the innermost electrons will be providing complete shielding, that is shielding effect, that is value is 1.00, that is completely 1 into the total electrons present inside are 6 plus 2 plus 2, that is totally 10 electrons. So shielding constant, that sigma value will be 1 into 10 is 10 plus 18 into 0.85. Where you can calculate with your calculator or any other method, but I'll show you a different kind of method, that I said in the before, consider this 0.85 in the form of decimal, So calculation part for 18 into 0.85 will be 18 into 17 divided by 20, where this would become 9 or 10. 17 9s are 153 divided by 10, that will be easily calculated as 15.3. So 15.3 plus 10, that is 15.3 plus 10 is shielding constant will be for copper, that is at 4s orbital is 10 plus 15.3 is 25.3, where the actual nuclear charge Z is equal to 29. So Z effective is given by Z minus sigma, that is Schilling constant. So it is given as 29 minus 25.3 is given as 3.7. So Z effective for 4s orbitals electrons is 3.7. And a little modified version of example is given, because in the question paper there might be possibility for any kind of confusions. So we will discuss Na plus or Cl minus, any positive charge ion or negative charge ions. So here out of this let's pick for example chlorine. So the question is calculating last electrons net nucleus charge, that is the Z effective for Cl minus ion, that is Cl minus ion. So write down the electronic configuration. Cl minus is one electron more than the actual chlorine atom. So chlorine has totally 17 electrons, but electron configuration should contain 18 electrons. So the electronic configuration will be 5 plus 1, and the modified rearranged electronic configuration according to Slater's rule is 1s3p6. So here 3d remains 0. Because n is equal to 1, 2, 3, and this the last one, last value for 3d. The calculation part of substituting values according to Slater's rule. The last electron is given as 3p6. So remove that, don't consider that last electron. So our available electrons for shielding is 5 in this and 2 here. So there will be totally 7 electrons, that is 1 minute, there is 7 electrons here, and 6 plus 2 plus 2, that is 10 electrons here. So here 7 electrons contributes 0.35, and the next n minus 1, that is, sorry for this, 6 plus 2, that is 8 electrons will be giving 0.85 value, and the innermost electrons at 1s2 will be giving complete shielding effect, that is 1 into 2. Again restructure calculation. 1 into 2 is 2 plus 0.85 into 8, that is 17 by 20 into 8, that is 4 2s are, and 4 5s are, 34 by 5 is 6.8 plus 0.35 into 7, that is given as 7 by 20 into 7, that is 49 by 2.45. So shielding constant is given as 2 plus 6.8 plus 2.45, that is totally 11.25. So Z effective is given as Z minus sigma, where Z is 17 only, not to confuse with 18, because negatively charged presence of electron is 18, but the proton present in the chlorine minus ion will be 17 only. So effective, that is the Z value will be 17 minus 11.25, that is given as 5.75. So there are plenty of examples, because but we can't be discussing each and every example. So calculate some few of the given example that I will be mentioning here. So try this example with your own practice, and we will be meeting in the next session with some other new concept. As this was the calculative portion, please do expect 2 marks question for this calculating Z effective, or combined question as for the 5 marks for stating Slater's rules and some other definitions.